So last session we stopped here with large scale GAN. And if you have noticed, we are trying to generate higher and higher quality images. We already solved the problem with the first paper on GANs, but then we were not happy with the loss function. We had some trouble converging or making them to converge. The quality, the images were low resolution. Now we are trying to generate higher resolution images. We have to modify our architectures a little bit. At the same time, we needed to come up with quantitative metric for comparing methods to methods. For instance, Fresher inception distance and inception score are two quantitative metrics for generative tasks. And we didn't have those. Today, we are going to continue with StyleGan. You probably have heard about it. What did we do with progressive growing? We had this architecture that we would take a latent Z, we would normalize it, and then we would push it through multiple layers of neural networks, and each one was operating at higher resolution, and you were progressively growing it. It was 4 by 4, and then you would do 8 by 8, and then you would do 16 by 16, up until 256 by 256. So you kept growing it. One criticism is that the latent that you're generating is coming from a normal distribution. Can you perhaps put a better distribution on Z? And that's exactly the idea here. Perhaps a better notation for this part of the paper would have been maybe W going in, being a simple distribution, normal and identity. And then as you push it through fully connected layers, it would give you a Z that is complex. But it's just notation. It doesn't make much sense. It's just a matter of preference. So let's say Z is a normal distribution and W is a complex distribution coming out of a nonlinear function. Now W is the one that is going to help us to introduce style in our neural network. And then I'm going to break apart different parts of the generator. So this is the main component. Z could be simple, W could be complex, and W doesn't have to be, these are actually not parameters. So this is also perhaps bad notation. These are not parameters of your model. These are, you can just call them Z prime. They're like your Z's. They're just coming out of a more complex distribution. So don't think of W as your weight. These are latent stuff still coming out of another latent variable. Okay, so far so good. There is some input to your architecture. There is also some other noise being injected at different portions of your architecture. What is going to go inside your synthesis network is a learnable tensor. And this learnable tensor is going to be shared. This is actually part of your architecture that you're going to be learning it. So in PyTorch, you're going to say that this is nn dot parameter of this size. And then you initialize it randomly, and then you let the gradients or let this tensor to have gradients. It means it is trainable. Okay, so the input to G is actually a constant thing, which is going to get trained. And the latent stuff are going to give you the style, and the noise is going to get injected to give you minor details of the generated images. And so far, so good. This idea is not new, and I want you to learn about it because it's a very useful technique. If you want to modify the style of the images getting generated, it's a good idea to inject the style through the mean and the variance of your normalization scheme. We saw this technique before. Previously, if we were trying to condition on perhaps classes, for instance, if you wanted to generate images of only cats from a particular class, then you would have these parameters to be dependent to the class. These would just be different for each class. Maybe you have different ones for cats, dogs, etc. Each one is going to have their respective mean and variance or a scaling factor. So this technique is not new. We can actually modify the style of generated images by modifying the variance and the mean. And this is just your usual subtracting the mean, dividing by the standard deviation. And this is instance normalization. And instance normalization, we can think of it as being batch normalization when your batch size is 1. So this is a powerful concept, and it's not from this paper, that you can actually inject style through the mean and variance of your normalization layer, in particular instance normalization. But what is this X? We usually have tensors when we are working with convolutional neural networks. We usually have tensors. This is the number of channels, and this is height and the width. And if you have noticed, and if you are using PyTorch, you have the number of channels first, and then you have your resolution. So this is PyTorch notation. If you are using TensorFlow, you have H, W, and C, and that's TensorFlow notation. So these people are using PyTorch. Okay, so far so good. What is Xi? You're gonna pick your channel, and then you're gonna end up with a matrix. So I is gonna index your channels, and then you're gonna compute your mean. This is exactly the same thing that you would do when you are doing batch normalization for convolutions. You have the averaging over the resolution. At the same time, you have the averaging over your batch size. In this case, your batch size is 1. There is no point in writing that anymore. Doing any summation over it. It's just the summation over your resolution. That's your mean. That's the variance. And these are the quantities that go in here. Mean and the standard deviation. Okay, perfect. Now the question is, where do you get these Y's? Where are they coming from? This is B stands for bias, S stands for scale, and then this is going to end up being channel-wise. So for each channel, you have a different Y. It means that if you have C channels, you need to have a Y vector that is C-dimensional, and you need to have a YB vector that is also C-dimensional. If you concatenate these two together, it should give you something that is 2C dimensional. And where do you get that? You get it out of this modified latent space with an affine transformation. An affine transformation is just vector matrix vector multiplication plus a bias. This is just a fully connected linear layer. And then that's going to give you your scale and bias. And it's going to be 2C dimensional. The first C of them, you're just going to call it YS. The leftover, you're going to call it YB. Okay, so far so good. Any questions so far? Was everything clear? Okay, cool. Now you're going to add Gaussian noise. The noise is going to be a matrix filled with random numbers generated from Gaussian distribution. That's just your Z. And then you're going to have different versions of it that you're going to inject at different blocks and at different layers within blocks. But then you want to have different variation for these noise levels because all of them have mean zero variance identity. You can modify the variance to be a learnable parameter. And then this way you're controlling the magnitude of the noise in a learnable fashion. And these are per feature. Remember, I was counting the C. So this is the channel wise. So per each channel, you have a different scaling factor. Okay, so far so good. Now we are in a place to explain this architecture. You have a learnable constant. You generate some noise. You have these B's. You multiply your noise by B. You add it to your constant. You push the output through add-in. Add-in is going to subtract the mean, divide by the standard deviation channel-wise. And then you get the mean and the standard deviation from this affine transformation operated on W. And then you do a 3x3 convolution. You do the same thing. You add the noise, add in, style. You're now at 4x4 resolution. You do a simple upsampling. So there is no transpose convolution going on here. It's just a simple nearest neighbor upsampling. And the role of upsampling is if you have a single pixel in the previous layer, it should end up where it should turn into 4 pixels in the output. And you're just copying that value and pasting it in those 4 locations. Convolution add-in, convolution add-in. We keep increasing, but then at the same time, you have that progressive growing idea in the background, training this network. And if you remember, we were trying to disentangle Z. We covered 2 papers on it. One was beta VAE, and the other one was InfoGAN. And it's very good if you can disentangle dimensions of your Z. It was very hard to do so. We had to write down complex looking loss functions. Beta VAE was okay. InfoGAN was a little bit more complex. But here with these affine transformations and the style mean and coefficient, you can start interpreting. If you inject noise at this layer, it's different from injecting noise at this other layer. If you inject style at a coarse level, it's going to end up being different from style at a finer level, at higher resolution. This is what it means to be more linear, less entangled representations. And so far, so good. Don't worry about mixing regularization yet. I'm going to come back to it. Don't worry about truncation trick. Let's see some generated images. Everything that you see in this figure is generated. Okay? So nothing is real. How do you combine them? Let's say you generate these images. If you want to generate those images after the training is done, you sample a Z from normal distribution, you normalize it, push it through this nonlinear function. That's going to give you a W. Save the W's. We're going to need them. For this image, you have the corresponding W. For this other image, you have the corresponding W. Save them. We need them. Do the same thing here. These are generated images. They have the corresponding W's. Let's save them. Now let's try to mix and match W's of images in the rows and columns. We can pick the W of this guy. Now you have the option. You look at this image here, and then it was being generated with some architecture. The W of this guy, you can inject it at these low resolution layers, and then the rest of them you just copy and paste. So some W's are coming from image of the woman here. Some other W's are coming from the image of that man. And the rest of it is just generate one image with different W's. And that's going to give you the image of a man in the style of this woman. Now you have the option to inject W's of this guy at different layers, at different resolutions. If you inject them at coarse resolutions, you are going to be changing coarse stuff. For instance, the color of the hair, the pose of the face. And these are what is happening. If you inject it at mid-size layers or mid-resolution layers, you are going to be transferring styles that are not so significant, but still are modifying your picture quite a bit. For instance, the forehead of this guy is being borrowed by this woman now, and that's going to give you a new image. If you go to the extreme and inject at the highest resolutions, then the identity of that person is the same. The face is the same. The hairstyle is the same. The pose of the face is the same. Nothing changes except for details, minor details of the hair color. So all you are doing in this figure is mix and match W's. Okay, perfect. If that is what you want to do during test time, it would be good for your neural networks to have seen that behavior during training time. And that's why you do mixing regularization. While you are doing your training, you have usually two Z's, push both of them through this neural network. You're going to get two W's, and then use them mix and match at different layers, inject those at different layers. So that's the role of mixing regularization. We saw truncation trick before when we were sampling from Z from a normal distribution, but then you would sample it from truncated normal distribution. If a sample is from the tail of a distribution, you just don't consider it. You go ahead and sample another number or another vector. Truncation trick is a little bit more difficult on the W layer. And for that, you need to compute the mean of this function. That's going to give you a mean here. And we know that the mean, there is no guarantee for it to be 0 anymore because it is being pushed through a nonlinear function. And then you can control your W's by this hyperparameter. You add the mean and then multiply by psi W minus W hat. Okay, if psi is 1, what's going to happen is this W bar is going to cancel with the other W bar, and then you're going to get your W back. Why do you do this? Because there is this trade-off between the quality of your images and their diversity. If you set psi to be 0, then your W's are always the mean, and therefore you're always going to be generating the same image. It's going to end up being less diverse, and it's going to have higher quality. In the other extreme, you can play around with your key C. If you set it to be 1, you're going to be generating a lot of diverse images, a lot of different faces. So this is a hyperparameter that you can tune. If quality is important for you, you're going to play with psi. If diversity is important, you're going to play with psi. Make it bigger. What is the role of a noise? It's going to go ahead and do fine details of your image. It's going to modify those. And that depends on where the noise is being injected. So the noise that is being injected at these coarse layers is going to have a bigger impact compared to the ones that are being injected at the finer layers. For instance, this is one of the ones that are being injected at the finer layers. And then you can see that each time that you have a different noise, you have a different hairstyle, but this is tiny difference in the hairstyle. If you inject it at a coarser level, you're going to have curls that are bigger or smaller if you inject them at higher resolution layers. And that was the role of noise. Any questions about StyleGan? Was everything clear? Okay, awesome.